All right, guys, today we're moving on to 4b.4, dividing complex numbers. Again, our mission here today is I can divide complex numbers by utilizing the conjugate. All right, I have no idea what conjugate is right now, but believe me, you're going to know what it is by the time we're done. It's a fun word to say anyway, conjugate. It just sounds good on the lips. So I can divide complex numbers by utilizing the conjugate. So first, let's back up and let's do some maybe some previous learning, maybe something you've never learned before. But I want to actually use something you're going to think, what in the world? This don't even have anything to do with complex numbers, but it's really going to come into play. So let's take, for example, I have 2 divided by the square root of 2. Now, in mathematics, sometimes there are some of these rules and some of these things that are impossibilities that the mathematicians get really worked up about, and they say, "Hey, this is just illegal. You can't do this. It's just something that it is not accepted." Okay, and one of the things that is not accepted in mathematics is to actually have a radical as a denominator. Okay, that is a big no-no when it comes to mathematics. And so mathematicians come up with this way to get rid of a radical that is on the bottom. And the way they do that is a process called rationalizing. All right, and we're going to really get into this in chapter 6. But I want to just show you this now because it does have some applications here. So the way they do this is they actually rationalize this denominator. So here's how this works. We have 2 over the square root of 2. One of the ways that you can get rid of that square root of 2, of course, is to square it. If you square the square root of 2, then it will get rid of that radical and it will make this answer just 2, right? I mean, we've kind of already learned that. Well, how in the world could I square this? Well, the way I could square this is I could multiply this particular number by the square root of 2 on the bottom, and that will get rid of that square root of 2. But the issue is, if I do it just to the bottom and not to the top, well, then it's going to make this totally different than what I originally started with, right? So it's kind of like the rule of equations. If I do it to one side, I have to do it to the other. Well, if I do it to the denominator, I have to do it to the numerator too, or I'm going to totally change my number that I'm starting with. So as long as you do it to both parts, then really I'm just either making it bigger, making it smaller, whatever the case may be. So really you multiply both the top and bottom by the square root of 2. And notice what happens here. On the top, I'm going to get 2 times radical 2, which kind of just gets squeezed together. And then on the bottom here, though, I've got the square root of 2 times the square root of 2, which is the square root of 4. And the square root of 4, obviously, is 2. So it goes right back to the 2. But notice I don't have the radical sign anymore. So again, square root of 2 squared is the same thing as 2. So it effectively does its job. It gets rid of that radical on the bottom. Notice what happens as well. I've got a 2 and a 2 here on both top and bottom. So if I were to take, for example, 5 divided by 5, then that just becomes 1, and really it just goes away, right? And 3 divided by 3 is 1, so really it just goes away. So what happens when you have the same number on top and bottom? Those things go away, and I'm just left with the square root of 2. So you're telling me, Mr. Hamilton, that 2 over radical 2 is the same thing as just plain old radical 2. Well, I want to prove it to you. So now let's go to Desmos here real quick, and notice I've already got it pulled up. 2 divided by radical 2 is 1.414213,562, right? You say, so what? Well, let's do this. Let's go ahead and do the square root of 2, and notice that I get exactly the same answer as I did a few minutes ago. So this, again, effectively rationalized this denominator. It got rid of having a denominator with a radical on it here at the bottom, okay? Now, again, you say, well, okay, why is that really important? Well, what I want you to think about is when we're talking about dividing complex numbers, is here I'm going to have something like this. For example, 6 plus 3i divided by 2 plus I. Well, I want you to think about what I really is. I, by definition, is the square root of -1. So really, on the bottom, I could say I really have 2 plus the square root of -1. I have a square root in my denominator, which is an illegal mathematic activity. Okay, so I cannot have that going on. Well, you may be saying, well, how in the world am I going to get rid of this? Like up here, I just multiplied it by the same thing and it got rid of it. Well, this is going to bring me to something else, and then we're going to come back to this problem, okay? Yesterday, when we were multiplying complex numbers for number 5 on yesterday's work, you had 25 plus 7i times 25 minus 7i, okay? When you had this particular problem right here, remember the way that we multiply complex numbers is just like we do when we have any other type of binomial. We have to use full, right? Which is basically just the distributive property. So I take this number times this, and this times this. So first, and then outer, and then inner, and then last. I'm basically just distributing each of these terms through the other binomial. Now notice what happens in this. We had 25 times 25, which is 625. We have 25 times negative 7i, which is negative 175i. We have 7i times 25, which is positive 175i. And then last but not least, we have 7i times negative 7i, which is negative 49i squared. Now just notice what happens here. There's a whole lot of magic that happens all here at one time. I want you to notice I've got some like terms here right in the middle, but notice what happens with those like terms. I have 175i minus 175i. Well, that just cancels out, okay? It just completely goes away. And then notice what I have left over here. I've got negative 49i squared. Now, we also already kind of established that I squared is the same thing as just plain old negative 1, because if I take the square root of negative 1 times the square root of negative 1, I'm going to get just plain old negative 1. So that means really what I have is 625 minus 49 times negative 1. Well, what happens when I multiply times a negative 1? All it does is it changes my signs. And so I end up with 625 plus 49, and it gives me the answer of 674. Hang on just a minute, Mr. Hamilton. You started out with a bunch of i's all up in here, and all of a sudden you get an answer that doesn't have an I in it at all, okay? The reason this happened is because this right here was like a difference of squares, okay? Notice these terms are exactly the same. The only difference is these symbols that are in between. I've got a plus here and a minus here. It's just like difference of squares that we did in chapter 4 already. And so you see that when I multiply by something that's a difference of squares, I get rid of all of my I terms, okay? So let's take what we learned up here about rationalizing square roots or radicals, and let's take what we learned here from problem number 5 on multiplying complex numbers and using full and difference of squares. Let's take all of that and let's wrap it up together to help us with this particular problem that we have right here. So I'm going to rewrite that problem again. Right down here, we have 6 plus 3i divided by 2 plus I. How can I get rid of this? Well, if only I could multiply by a difference of squares, just like I did on this particular problem right up here, then all of a sudden I could get rid of this. Well, ladies and gentlemen, I want to introduce you to the conjugate. Okay, the conjugate is basically just the opposite of what this is. Okay, so in other words, just like I multiplied a few minutes ago by radical 2, in this case, I'm going to multiply times 2 minus I, okay? And if I multiply the bottom by 2 minus I, then I have to multiply the top by 2 minus I. You say, why are you doing that? Well, again, when I multiply this out, when I FOIL this out, right, it's multiplication in between, I know that it's going to get rid of the I. And again, if I do it to the bottom, I have to do it to the top. So this is called the conjugate, okay? The conjugate is just basically making a difference of squares so that you can rid yourself of this I. So notice what happens here. And we're gonna start, I guess, with the top. Again, think about this as just being 2 binomials, this being 2 binomials, and you're just multiplying them together. It goes right back to the work we did yesterday. So if we do 6 times 2, I'm going to get 12. 6 times negative I is going to be negative 6I. 3I times 2 is going to be positive 6I. And 3 times negative I, 3I times negative I is negative 3I squared. All right. Oh my goodness, look at what happened here. Now, this is not going to happen every time. But let's go ahead and do our fraction bar. We'll go ahead and do the bottom, and then we'll think about the rest of it. So on the bottom, remember, when I multiply this out, I don't have to do full-blown full because the middle terms are going to go away anyway. So remember, all I have to do here with the conjugate is just do FL. So I'm going to do first, and then I'm going to do last. So 2 times 2 is 4. And I times negative I is negative I squared. Now let's kind of clean this up a little bit. So remember, I've got some like terms here in the middle always, unless I'm doing FLA. So negative 6I plus 6I, just so happens this goes away, okay? So then think about what I have left. I have 12 minus 3. Wait a minute, I've got an I squared here. Remember, what is I squared? I squared is the same thing as negative 1. So I've got 3 times negative 1, and what does that actually do? Okay, we'll look at that here in just a second. Well, actually, I want to look at it now, because that just makes that a positive 3, okay? So really what I have is 12 plus 3, which equals 15, okay? I just brought my work down here. So then that helps me down here, because now I have 4 minus a I squared. Well, 4 minus I squared is just 4 minus a negative 1, right? So 4 minus a negative 1 is a positive 5. So really I have 15 divided by 5, which just comes out to an answer of 3. Now, it's not always going to look that way, but this particular example come out to where I didn't have any i's at all. Okay, I want to work out one more example. I don't want to get this video super long, but I want to at least show you enough that you'd be able to do it. So let's call this example 1, and we'll go on down here and we'll do number 2. Okay, number 2 is 7 plus I divided by 4 minus 3I. Now, again, we don't usually write our problems this way. When we go into high school mathematics, we go ahead and write that as a fraction. We understand that a fraction is nothing more than a division problem. So 7 plus I divided by 4 minus 3I. And now how am I going to get rid of this I? Say it with me. Conjugate. Okay, I want to multiply by the conjugate. Well, what is the conjugate? The conjugate is basically the same terms, 4 and 3I. The only difference is it's going to be the opposite. So this one is negative, so I'm going to make this a positive. Okay, and whatever I do here, I've got to do on top as well. All right, and now I'm just going to multiply straight across. Just like I multiply fractions, I'm actually multiplying two binomials against one another. Okay, so 7 times 4 is 28. 7 times 3I is 21I. I times 4 is 4I. And I times 3I is positive 3I squared. Okay? On the bottom, remember, the whole reason I did this was to get rid of my i's. So now I can just do FLA, or FL. 4 times 4 is 16. Negative 3I times positive 3I is going to be negative 9I squared. Okay? So again, let's look at our like terms. We've got some like terms right here on the inside. So let's take care of those first. I'm going to move my work down here just so we got, actually I can just move it over. So we've got 28 plus 25I plus 3I squared. So I want you to start getting into a mode now to where you think, okay, wait a minute, I squared is negative 1. So really what I have here is 3 times negative 1. 3 times negative 1 is just going to be a negative 3. So notice if I've got a number times I squared, it's basically just going to be the opposite of whatever I have. Notice I have positive 3. I multiply by I squared, I'm just going to get a negative 3. Okay? Now, over here, I have 16 minus 9I squared. Again, I squared is negative 1. Anytime I multiply negative 1 times anything, it's just going to change the signs. And so instead of a -9, it's just going to be a +9. Let's just think about what we have here now. Let's take some like terms again. We're on the home stretch. Hang with me. 28 minus 3 would be 25 plus 25i over 25. Interesting. So what I want you to think about is, remember, our standard form of a complex number actually has a form of a plus bi, right? This one right now doesn't really look like that, but I want you to realize that this 25 actually applies to both of these numbers, okay? So I could just as easily rewrite this as 25 over 25 plus 25i over 25, okay? I just took this big fraction right here and I made it into more something that looks like my complex form that I should have. But notice what also happened here. What is 25 divided by 25? Well, that's just 1. And what is, here again, I've got 25 divided by 25. What happens to this 25 divided by 25? It just goes away and gets canceled, and the only thing that left is I. So, ladies and gentlemen, after all that work, my final answer is 1 plus I, okay? Well, hopefully this has been helpful to you. Again, this is not really that complex. It's a little harder than maybe other stuff that we've done in this particular chapter, but you're basically just making this a multiplication problem by using the conjugate and then just doing the math work that needs to be done. If you need any help, please reach out to either me or Miss Willer, and we'd be glad to help you out with this. Thanks.